Hi, my name is Vitor, and in this video I'll talk about Atlas, a new consensus protocol specially designed for planet-scale systems. First, let's start by deconstructing the title of our paper. We replicate data for fault tolerance. As an example, consider this case where we have 3 replicas and one user accessing the system. If the replica being accessed by this user becomes unavailable, the user can fail over to another replica. This means that a replicated system can keep answering to user requests despite the failure of some replicas. And we do this on a planet scale to minimize latency, which may happen since users can access the system through the closest replica. Since with replication we have several copies of the data, possibly being modified by multiple users, it comes the question of how consistent is the data being replicated. In this paper we consider the strongest consistency model, linearizability, in which the system behaves as a single copy, meaning that replication is transparent to application programmers. And the classical way of implementing linearizability is through state machine replication, or SMR. In SMR, the system is defined by a state machine, and there's a protocol that determines the order in which commands are applied to the state machine at each replica, making sure that replicas stay in sync. And the question we set out to answer was, can we attain low latency with planet-scale SMR? And for that, we have identified 3 key properties. First, in order to process a command, the protocol should contact small quorums that are nearby. Moreover, the protocol should be leaderless. In leader-based protocols, when the leader fails, the system is unavailable until a new one is elected. Leaderless protocols don't suffer from this problem, as there's no single point of failure. And since any replica can process commands issued by clients, we also get load balancing. Finally, there are no additional hops to reach the leader, which means that we don't have clients that experience high latency just because they are far away from the leader. The third and final property is that commands should be processed in a single run trip. To attain low latency, it's not enough to contact small nearby quorums. These quorums should be contacted only once. And those are the 3 properties. Now we'll check if existing SMR protocols have them or not. Paxos is a leader-based protocol, and since only f+1 replicas, where f is the number of allowed failures, need to be contacted by the leader, the quorums are small. However, commands are processed in a single run trip only when the client is collocated with the leader. Paxos is a leaderless protocol that requires large quorums containing 3/4 of all replicas, and commands are only processed in a single run trip if there are no conflicts. And we say that 2 commands conflict if, for example, they access the same key in a key-value store. Before telling you about Atlas, let me first talk about an experiment we ran in Google Cloud Platform. In this experiment, we had each data center periodically pinging the remaining data centers and recording the ping latency. After 3 months, we collected all this data and searched for link slowdowns, where a slowdown would be a ping returning after a few seconds. We observed that when these slowdowns occurred, they were never incident to more than 1 data center at a time, from which we can conclude that in a planet-scale system, it is not necessary to assume high values for f. And for that reason, in Atlas the quorum size is a function of f, which allows Atlas to have small quorums for small values of f. Atlas is also leaderless and can process most commands in a single run trip, what we call a fast path. And this is possible because Atlas employs a flexible fast path condition that allows the fast path to be taken even when conflicting commands are submitted concurrently. and now we'll see that fast path condition in action. In this example, we have 5 replicas, the number of allowed failures f is 2, and we have 2 conflicting commands a and b that are submitted concurrently. Since the quorum size in Atlas is a minority plus f, when process 1 submits command a, it contacts 4 processes including itself. Similarly, when submitting command b, process 5 does the same. These white boxes contain the order in which processes 2 and 3 and 4 receive commands A and B. And we have that processes 2 and 3 receive first A then B, while the opposite happens at process 4. Now, when a process receives a new command, it reports the set of conflicting commands it received before. So for command A, processes 1, 2, and 3 report an empty set, while process 4, which received B before receiving A, it reports a set containing conflict B. For command B, processes 4 and 5 report an empty set, while processes 2 and 3, which received A before receiving B, report a set with conflict A. In Atlas, the fast path can be taken if every conflict was reported by at least f processes. At process 5, we have that conflict A was reported by 2 processes, and for that reason, process 5 can take the fast path, committing the commands. On the other hand, at process 1, conflict B was reported only by 1 process. Since we don't have f processes reporting this conflict, process 1 needs to take the slow path. In Atlas, this means contacting f+1 replicas, and only then it is safe for process 1 to commit command A. Note that previous protocols like Ipaxos require that all processes report the same set of conflicts. For that reason, in Ipaxos, the slow path will be taken for both commands in this example. These conflicts that are committed are then used to determine the order in which commands are executed. In this example, we have 3 commands, A, B, and C, and since both B and C declare A as a conflict, A must be executed before them. However, commands B and C include each other as a conflict, so we have this cycle. We break cycles following some deterministic order on the identifiers of each command, so we have 2 possible execution orders depending on the identifiers used for B and C. Since all replicas will reach the same conclusion, this ensures a consistent execution order across all replicas. In the evaluation, we have considered 2 planet-scale scenarios. In the first one, we gradually bring the system closer to clients. Clients are deployed at 13 data centers, and we expand the system from 3 to 13 replicas. In the black bar, we have the latency that will be provided by an optimal leaderless protocol. Atlas f=1 is at most 13% above this value. Moreover, Atlas improves its performance as it is deployed closer to clients, cutting down latency by 40% when going from 3 to 13 replicas. In the second planet-scale scenario, the system is expanded in order to serve new clients on new regions. In this case, clients are always collocated with a replica, and again we stretch the system from 3 to 13 replicas. We plot the latency penalty with respect to the optimal performance. Ipaxos hits this optimal value with 3 and 5 replicas, but starting from 11 replicas, Ipaxos has a latency penalty of at least 50% due to the large quorums it employs. Starting from 9 replicas, Ipaxos' performance degrades quickly since the leader cannot handle the increasing loads. In contrast, Atlas is able to cope with the growth without degrading performance. Client perceived latency is within 4% of the optimum with f equals 1 and within 26% with f equals 2. Please check the paper for more details. There, we show that Atlas recovery mechanism is much simpler than previous protocols. You'll also find two optimizations that speed up command execution and a comprehensive evaluation where we cover the likelihood of fast paths, availability on the failures, and YCSP. There's also an extended version on archive where you can find the proof of correctness. To summarize, Atlas exploits the fact that in planet-scale systems, concurrent data center failures are rare, where these failures can manifest through link slowdowns or actual machine crashes. Atlas is the first leaderless SMR protocol that allows configuring the number of replicas independently of the number of allowed failures. It employs small quorums for small values of f, and its flexible fastpath condition allows a high percentage of commands to be processed in a single round trip. And that's it for this video. If you have any questions, please contact me at any of these two. Have a nice day.